So you are welcome to this virtual lecture. So like I said, I'll be sending some materials to cover the chapters that we hadn't yet covered, beginning with chapter 5, which is discrete probability distributions. So to understand what probability distribution is, first of all, you have to understand what a random variable is. So basically, a random variable is something that numerically describes the outcome of an experiment. And an experiment could be anything that generates different outcomes. For instance, if you flip a coin, it is basically an experiment which can have two outcomes. You could have heads or tails. So what the random variable is basically that thing that can hold that value of heads or tails. So for instance, if you flip a coin, you have heads or tails, and we say it's a numerical description. But the values do not necessarily have to be numerical. For instance, if your values are heads or tails, you can actually turn these into numerical values by assigning, for instance, heads, a 0 for heads or a 1 for tails. So that variable is discrete. When you say it is discrete, it means that all the possible outcomes can be enumerated. You can fully describe the sample space. So for instance, when you flip a coin, you know it's going to be heads or tails. If you do it twice, then the sequence could be heads, tails, tails, heads, 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 and tails, tails. So you have two possible outcomes. So if you have a situation where you can fully describe the possibilities, when you can fully describe the sample space, then we say that you have a discrete random variable. So a discrete random variable will be able to take on a given sequence, a specific sequence of values, and those values can be fully enumerated. It doesn't matter how many they are, but if you have a situation where you can fully enumerate the entire sample space exhaustively, then you have a discrete random variable. So examples of situations where you have a discrete random variable. For instance, you could maybe you're contacting 5 customers, and the number of customers is going to be a random variable. So the number of customers that are going to place an order out of the 5 is going to be some number from 0 to 5. So it's going to take on a very specific, there's a specific list of values that this variable, which is the number of customers who place an order, can take, and you can fully describe the sample space. You can fully describe the sample space. There's no value in the sample space that you do not know. Then you could have, for instance, inspecting a shipment of 50 radios. If you want to determine the number of defective radios, again, it could be value from 0 to 50. So you do realize that actually these are discrete random variables actually taking on integer values. Yeah, they actually take on integer values. Then you can see selling an automobile. So the gender of a customer is going to be male or female. Yeah, and we said you could express this as numbers. So as a key characteristic is that you can see you can actually evaluate, or you can enumerate, you can list all the values. Yeah, if you're in a situation where you can list all the values, and the variable can take on any one of these values, but you know exactly which values you can take on, then that is what you call a discrete random variable. But you could also have a continuous random variable. With a continuous random variable, you do not have value can take on any value within a given range, but you cannot fully enumerate all these values. It's not possible for you to fully enumerate all these values, and this usually happens if you're dealing with real values or things like physical measurements. For instance, if you are dealing with something like height, or time, or weight, or distance, or temperature, then these will normally be described by continuous random variables. And these are best described in the previous situation when you had a discrete random variable. The probability distribution function is going to be basically generating a list of values. It will generate, I'll talk about what a probability distribution function. So there's a function which generates these values. Yeah, it's a function which generates these values, and that function is going to generate a list of values. Yeah, but in this case, because you can take on any value within a given constraint, then it makes more sense to actually use to describe this distribution using an inequality. For instance, where the value is x could be greater than 0, or if the value could be greater than 0 or less than 1. So you can look at some examples. For instance, if you're operating a bank, yeah, so the time between customer arrivals in minutes could be any number, yeah, could be any number greater than 1, yeah. So the time between 2 consecutive customers could be any number greater than 1. So this is you cannot enumerate all the possibilities. You cannot say it cannot go beyond maybe 100 or and so on and so forth. So it could be well, if you're going to log, maybe we might have an upper limit. But even when you have an upper limit, the time could be 1 minute, the time could be 1.1 minutes, the time could be 1.11 minutes, the time could be. So you get my drift. So usually, if you're dealing with a real value, you're going to have this kind of situation, because you cannot fully enumerate, because you can always have, you know, an additional decimal point and so on and so forth. If you find for instance, the number of ounces in a soft drink can, yeah. So if you measure different bottles of soda, you find that this value is between some limit. It's greater than 0, obviously, because there's some soda in it, but it's going to be less than some maximum. But in between here, it can actually take on any value. It can take on any value. It could be 0.1, 0.11, 0.12, and so on and so forth. So there's an infinite. In this case, the sample space is actually infinite. The number of values that you can actually take on it is and you cannot simply list the values out. It will not be feasible for you to list all the values out. So if you have a situation like this, and you can see this will apply naturally if you're dealing with real values. If you're dealing with physical measurements, it's going to be, it will naturally be the case that you are dealing with a continuous random distribution. So you can just go through this exercise. For instance, we considered an experiment of tossing a coin twice. So I've already mentioned this. So this is a no-brainer, yeah? So if you want to list the experimental outcomes, it's going to be heads or tails, right? Because you're flipping a coin, if you're flipping a coin twice, then the sample space, I think there was a question about this in the last test on probabilities. So the sample space is simply going to be the number of outcomes to the power of the number of steps. So the possible outcomes are 2, and the number of steps in this multi-step experiment is also 2. So you have 4 possible outcomes, and outcomes could be heads, heads, tails, heads, tails, tails, and tails, tails. So you have your 4 possible outcomes. So to define a random variable that represents the number of heads occurring on the 2 tosses, if you have some x, yeah. If you have some x, then you can have x is equal to 1. It's going to be a list. X could be 1 or 2, yeah. So if you have an f of x, this would basically be a step function. For those of you who did some level maths, it should basically be a step function where f of x could be 1 or could be 1 or 2, because you could have 1 or 2 heads depending on the sequence that comes out, because the possible sequences are tails, heads, where you have 1 head, heads, heads, where you have 2 heads, heads, tails, where you have, again, you have 1 head. So you either have 1 or 2 heads, yeah. So then show what value the random variable would assume for each of the experimental outcomes. Again, you can, I've just listed it verbally. So the final question is, this random variable discrete or continuous? What do you think? I've already given you the answer. So if you look at the second exercise, we want to know, maybe let me just do some Excel here. Yeah, so this is what we were doing. So we said if you have a 1 toss, you have heads and tails. These are the possible outcomes. If you have two tosses, then you could have a tail, then a head. You could have a head. You could have a head, and then a tail. You could have a tail, and a tail, and you could have a head and a head. So if you're looking for, if your random variable is basically the number of heads that you're going to get. So the possible values, like I said, you have if you have this kind of permutation here, you have only one head. In this case, again, you have one head. In this case, you have no heads, and then in this case, you have, or we should have. So I was actually giving you something not right. You have three possibilities, and then you have two heads. So you actually have three possibilities. So you have, so X could be 1, where you have tail head or head tail, or X could be 0, or X could be 2, the number of heads. Yeah. So these are the possible outcomes that you have in this discrete probability distribution. So it is discrete because you can actually list out all the possible outcomes. So this makes it a discrete distribution. So anyway, we can move on to the next. So if you consider the experiment of a worker assembling a product, so you define a random variable that represents the time in minutes required to assemble the product. So the time in minutes required to assemble the product, maybe before we leave here, I say this would be basically, if you are doing an f of x would be something like, we used to have this, for those who did some, just a minute, do I remember where to get this? So you want to get a big brace. So you want to get a one-sided brace. So you want to have one of these, yeah? So then you have X could take on these values. You could have a 0, a 1, a 2. So this would basically give you the probability, rather this would basically give you the the different possibilities that you could generate. Let me just look this up. So I just want to look up the oops, no internet here. So I just wanted to look up the syntax, but it's not relevant to this lecture for a step function. But anyway, so let's move on to the experiment for a worker who is assembling a product. So when you're assembling a product, you want to define a random variable that represents the time in minutes in minutes required to assemble the product. So in this case, your X is going to be, because the time to assemble a product could be anything greater than 0, depending on the assumption you make. Of course, it could be the case that, for instance, the product is already assembled. Maybe we exclude that case. So in general, you have your X which is greater than or equal to 0 and less than or equal to. I think this would basically be, because it is possible. So this value is going to range from any value from 0 to infinity. Infinity meaning that you did not complete, that you never complete assembling the product. So if you have such a situation, then this is basically, do you think it's discrete or continuous? So I'm giving you some time to think about it. But basically, what you have is a continuous probability distribution. It's basically a continuous. It's a continuous probability distribution. Yeah. So just back. So let's just head back to the exercise. Yeah. So this is basically going to be a continuous frequency distribution, because you cannot really enumerate all the possible values. So let's look at exercise 3. When you have 3 students scheduled who have scheduled interviews for summer employment at the Brookwood Institute, so in each case the interview results in either an offer for a position or no offer. So the experimental outcomes are defined in terms of the results of 3 interviews. So you want to list the experimental outcomes. So you have 3 students scheduled for interviews for summer employment at the Brookwood Institute. In each case, the interview results in either an offer for a position or no offer. So again, in this situation, it is actually possible for us it is actually possible for us to enumerate all the possible outcomes. It is possible for us to enumerate all the possible outcomes because you have 3 interviews. You have 3 interviews, and each interview can result in an offer or not. So again, you have the number of possibilities is 2. So the number of possibilities is 2. You can either offer or not. And the number of outcomes, rather the number of steps or different experiments is 3. So if you have 3, is the number of different steps. It's again a multi-step experiment, and the number of possible outcomes is 2. So you have 9 possible outcomes. The number of possible outcomes is 2, and the number of steps is 3. Yeah. So you have 8 possible outcomes. Because you can have offer, you can offer everybody, you can offer, deny offer, you can offer, deny offer, you can offer, deny, you can deny, offer, you can. So I'm going to just, you have D or D. Have I finished them? So there's 1, 2, 3. D or D, then you can offer, deny, offer. Was that deny, you can offer, deny. Then you can deny, offer, deny, offer. So let's see. 1, 2, 3, 4, 5, 6, 7. So there's an 8th one. Which one am I forgetting? So you have offer, deny, offer. Do you have offer? Do you have ODD? Offer, deny. Deny, offer, deny, offer, deny, deny, offer. Okay, maybe let me just leave this as so I think I can leave this as homework for you to figure out the remaining permutation here. So these are basically the possible outcomes. Yeah, these are the possible outcomes. So the fact that we can actually outline all the possible experimental outcomes basically means that this is going to be a discrete random variable. So this is basically a discrete random variable. So if you want to show the value of the random variable for each of the experimental outcome, so if the random variable we're tracking is either offer. So for instance, the random variable that we could define could be the number of offers, yeah? Could be the number of offers or the number of denials. So if you look at the number of denials, then the number of denials is going to be some list of values. It is going to be some list of values, and we can construct some kind of probability distribution function, which I said is going to be a step function that defines the probability that comes out of this experiment. I have already actually, I told you I was going to look up the syntax for a step function. I've already done that, but I'm going to go back into that in the next section. But let's look at the next exercise. Yeah, so in this case, we have, suppose we know home mortgage rates for 12 Florida lending institutions, and we assume that the random variable of interest is the number of lending institutions in this group that offers a 30-year fixed rate of 8.5% or less. So what values may this random variable assume? So it's basically going to be a number. So we want to know out of these 12, yeah, how many actually fulfill this condition. And again, this could be a number. So this again is going to take on a very specific list of values. So this could be anything from 0, as in no organization, no bank actually meets this criterion, or all the banks meet this criterion. So it could be any number from 0 to 12. It could be any number from 0 to 12. But the thing is, we actually know the numbers, yeah? So if you know the numbers, then, because we can actually list this out to 0 to 12, right? So that makes it a discrete probability distribution. That will make it a discrete probability distribution.